Now today we're going to, so time evolution is actually one of the most fascinating aspects of quantum because it's relevant. I mean, you're doing your experiment over time, right? It's really the most important thing that we perceive. So it's kind of a big failure not to talk about. So sometimes people don't even get into time-dependent quantum and quantum 1, and they save it for quantum 2. We don't have a quantum 2, so that's a bit of a problem. So anyway, and some of the things we're going to cover today are pretty awesome. Just a reminder, just to remind you what we did, because I'm going to use this at one point, that we have this classical Poisson bracket thing, which gives me the time derivative of a function. And for any mechanics function, remember I'm talking a rocket ship, a ball in a miniature golf course. Everything's going to be a function. Whatever I'm interested in, like angular momentum, will be a function of coordinates and velocities, right? Remember this velocity. Okay, cool that. And recall that this is equal to the F, dq, dh, dt, and then you just permute that df dt. Now I'm actually going to use this at probably an electron like about Monday. I'm going to use that. And your book is also, one reason I went to cover this is because your book just goes off and off and off and off and off and off and off on it all the time through this chapter. Now again, this is for a ball in a miniature golf course, but it turns out that there's the classical, and here's the quantum mechanical and a commutator. And as much as commutators, these are kind of painful. They're always, I hate seeing commutators. It's just like, oh, it's one of those damn things. It turns out it's going to be terribly important for most of this discussion. Anyway, so this connects the classical to the quantum. And again, because of this property right here, so this is the evolution of the operator in time. Not today's lecture, or maybe even Friday, but I'm going to be using this quite a bit. So this is why commutators appear frequently in time-dependent quantum. Let's see, the other thing we talked about is that everything I've been doing thus far has been this, where t0 is, of course, 0 seconds, because why not? So if you apply a unitary operator, you're going to evolve that in time. I'm using the book's notation. Recall that that notation will change later on when we just decide that t0 is 0. It's, again, just a little bit of a flaw of the book, of course. Here, let me make that concrete. Let me apply the operator there. Okay, so there, that's better. Let's see. Then we talked about some properties of the operator. Of course, I'm using the letter U. It has to be unitary, and that's because the inner product of a state with itself now and then needs to be 1. It needs to be normalized. It's, again, thinking of like how much of it is there, 100% 1. So recall that. That's, of course, because if you time evolve abroad, you've got to have the adjoint time evolve a ket. Sorry, it should be alpha, right? And then this is the inner product of the state with itself. And again, of course, that but at a later time, of course, it's still going to be normalized. Okay, now this one, and I'm repeating still what I did last time, but this one is horribly important. So sorry, this was. There was another point, which was that as time goes to t0, that nothing changes. I'm not going to write that down again. I wrote it down last time. Okay, now one thing I want to point out that I think this was actually point 3, so sorry about that. Okay, so this ends up being horribly, horribly important. I'm going to use this property to solve everything today. And this makes sense. I think that this just comes about from, this is phenomenological technically, but this just inherently makes sense. If you're going to move something from 0 to 1 femtosecond, and then from 1 femtosecond to 2 femtoseconds, that should be the same thing as just moving forward from 0 to 2 femtoseconds. I mean, how could that not be true, right? So that's just horse sense. What I want to point out is that this is unbelievably crucial. I'm going to be doing all my derivations with this today. So, and again, it was 0.3 last time. I'm not bothering to point out, I think 0.1 was that if t is 0, then nothing changes, which is, stupid to the point I don't really need to bring that up. Anyway, so now recall, and I've been saying this for some time, that translation operator was just 1 minus, we had some nebulous operator k, which ended up being after some hideous proofs, p over h bar, and I spent like a whole day doing that proof, which I really just did for practice, and so that has value, obviously. Now for time evolution, guess what? I'm going to say that the operator is 1 minus I, some operator, and it will evolve things over a very short dt period of time. So some other properties are, and I'm not sure why this is unnecessarily, that we assume that the operator is Hermitian. I forgot why we need that, but anyway, that's part of it. And whatnot. Let's see what I want to do here. So the justification for this is because if you do this, okay, let's make sure this is 1. Remember I told you this is identical to what we did with translation, and I told you how part of this bothers me. Okay, so the adjoint is plus, the operator is minus, and we know that because, so remember that we use this relationship to figure out what the adjoint is, and we know that's because this ends up being, 1, I'm going to start with the letter I, I wrote I, 1 plus let me give you some notation in case you haven't seen this before. You write this little fancy O. Okay, so what that means is it's 1 plus terms on the order of dt squared. That means that there's a dt squared in it. And we just say, I think the book has that symbology. It's something I see frequently, so I thought I'd take the opportunity to show that. I don't know if I've shown that before. Okay. Also, point 1 that I didn't write down, if dt truly is 0, then the operator is the number 1, which doesn't do anything, but that was what it was required to do. Okay, so again, this is just justification for that this thing looks okay. Now, instead of spending a day figuring out that k is momentum over h bar, and therefore this unknown operator is whatever, the book, and I agree with, again, I don't think we need to blow out a whole day trying to figure out what, like we did there, when clearly Hamiltonians are crucial to time evolution. And so let's just assume that the operator is actually the Hamiltonian operator, which of course is Hermitian because energy is a measurable, energy is a real thing. I don't mean real like it really exists. I mean it doesn't have the letter I in it. So H is Hermitian, and there you go. So therefore U T0 plus dt, T0 is actually 1 minus the Hamiltonian over h bar dt. And of course, let's see h bar. Now, Hamiltonian's return energy, dt is time. So you better be divided by something that has units of time of energy seconds, which is h bar. H bar has units of joule seconds, and then h dt has units of joule seconds. Recall that's because you two should remember, my undergrads, this is something I beat the hell out of, excuse my language. In PChem 1, I go over unit analysis like crazy. 1 has no units, so that can't have units either. So that's why the h bar is there. Again, hand-wavy justification. Okay, so cool that. Now let's get into the details. All right, the first thing we want to do, recall that once I introduced this translation, moving things an infinitely small amount left or right is not useful. Moving things forward an infinitely small amount of time is not useful. The trick was to raise this to the nth power and just do it over and over and over again, and do it an infinite number of times, and then this 1 over infinity value times infinity ends up being finite. Okay, problem. You can't quite do that here. That sucks. And that's I think the reason is that the Hamiltonian could be time dependent. That sucks. If the Hamiltonian is time dependent, then you can't apply the same thing over and over again because over time it's changing. So remember, if I'm just going to write this down in parentheses like literally an infinite number of times, the operator can't be changing, right? Because what I'm doing is I'm going to use an identity, which is e to the I p over h bar x, and that's what this ends up being. And so the x is not dx anymore, so I can translate it a finite amount of time of position. And if I want to translate this a finite amount of time, not dt, which is 0 basically, I want to raise this to the nth power, but that assumes the Hamiltonian is time independent, and it may not be. And that's where we get a little bit of a problem. So I'm going to deal with that. But it turns out, let me just tell you, it turns out that if the Hamiltonian is time independent, and I raise that to the nth power and take a limit to infinity, so let me just tell you what the answer is. I'm like professionally negligent to tell you this. It turns out that this is the case. So if you're going to move things forward, not here, let me make that a little bit more generic. If you're going to move something finite, it bothers me that that h bar is there. There we go. It bothers me. Anyway, so if you're going to move something forward in a finite amount of time, you can raise this to the nth power, take a limit to infinity, and find that this is the case. So I've got to have that closing bracket or the world explodes. Anyway, okay. Now, it turns out, here's the approach. So, the one thing I want to warn you is that what I'm going to do today is going to be kind of complicated. And if you're reading your notes, and you're only reading your notes, you're going to get lost. Because the nuances of why I'm doing what I'm doing are as important as what I'm doing. All right, so what I'm going to do is I'm going to solve this. I'm going to work with this as though the Hamiltonian could change with time. And I'm going to derive what is one of the most complicated expressions that exists. And then I'm going to simplify that expression if time is time independent. Okay, so anyway, that's what I'm about to do. Okay, the next thing to note is that Hamiltonians that depend on time, that would be something like, let's say you put something like an electric field, that would be time independent. But now imagine it's like I have two plates, and imagine it's on some kind of motor, and so it's rotating. That's a time dependent Hamiltonian. You may also recognize that a time-varying electric field is a photon. So, if I have light impinging upon a molecule, I got myself a time-dependent Hamiltonian, right? So that's why I don't want to, on day one, assume that Hamiltonians are time-independent, because there's lots of reasons why they may not be. Okay, now the next thing to note is that I told you that this thing is crucial. Okay, so we're going to put a star, put a big star by this, and I'm going to write that down again. So again, what I'm going to do is I'm going to work with this SOB to get dt to not be dt. I want it to be a finite amount of time, not a 1 over infinity amount of time, which is a good start, but doesn't really get me anywhere. Okay, so that's the purpose. All right, now what I'm going to do is, again, I'm going to work with that, and I'm going to not write it quite the same way. I'm going to write it in a way that's a little bit more useful. Sorry. The point is not to, you'll see what I mean here in a second. The point is not to have a T naught. Okay, now how do I, notice that I've moved forward, not T naught plus a very small element. I've moved a finite amount plus a small element. Now how did I do that? Right, so this is like weird, because this is not T naught plus T dt. Anyway, so let me show you how I do that. That'll make more sense. Okay, let's see. Okay, all right. So yeah, I'll break this down. So again, I told you that the expressions I write are going to be kind of confusing until you hear an explanation. Okay, let me point out that this thing, I don't have an expression for this, but that's what I'm looking for. This is the target. You see what this does? This operator is taking the state at t0 and evolving it, not dt, but t. You know, not 1 over infinity seconds, but maybe more like 10 femtoseconds. And heads up, I would never use a second to represent a finite period of time when I'm talking about molecules or electrons. Femtoseconds are very long periods of time for molecules and especially electrons. So when I say I want you to get used to that. So when I say finite time, I'm never going to say 1 second, because that's eternity. That's the age of the universe times a billion to a molecule. 10 femtoseconds is like a moment to a molecule. It's a finite moment. Okay, so this is what I'm actually looking for. Now, look at this. This takes time t and advances a dt. All right, so this is what I know. I know what this is. Right? This is the thing that I just wrote down a minute ago. All right, that operator takes time and advances it a terribly small amount. This is what I'm actually trying to figure out. This takes t0 and advances it a finite amount of time. Okay, but this is still whatever the hell this is. Okay, the result. All right, now that I have this is really cool, by the way. I hope you appreciate this. This is neat. Okay, so I'm going to take this thing, which is advanced. Wait a minute. Yeah. I want to make sure I got it right. Okay, what I'm going to do is I'm going to multiply this through, and then I'm going to bring this thing over here. Oh, it needs a little hat. It's missing its hats. Little hat. Make it hat. It's a hat. There we go. Okay. Minus I and H bar. Okay. All right, so like middle school simple. All right, notice what I've done here. This is an advancement in dt. Right, so this is a partial change. This is just a partial change in, right? These are only different by some dt 1 over infinity amount. So the difference between the two is just the change in dt. And I can use, instead of like a partial, instead of the delta, like, this is final minus initial, I can use a partial symbology because they're 1 over infinity different, right? Because dt is 1 over infinity. Okay, so I can now use the language of partials to represent this. Okay, now look over here, I've got a dt. There's I over h bar Hamiltonian. Okay, now I've got a differential equation. Yeah, there you go. So differential equations, in fact, of all differential equations, nominally the derivative of something is equal to a function should be unbelievably easy to figure out. Of all the differential equations, this is like nothing. What I don't like is all these symbologies. When I see something like this, which is, oh, this is very easy, it's a simple differential equation, but I see little hats or things are bold, that's when I know, no, this actually isn't going to be easy at all. That part looks easy. These little hats make me freak out. Anyway, there's some bloody honesty for you there. Okay. First trick. Okay, next step. Okay, so I'm going to take a little break here. Okay, what I'm going to do with this is I'm going to integrate it. Okay, so what I'm going to do is I'm going to bring, no, I won't. I will leave that IH part there. What I'm going to do is I'm going to integrate from T naught to T, I'm going to integrate dt, and, okay, now, I'm going to integrate this thing, but there has to be some engineering of the expression. So look out for this kind of stuff. Note that I am going to solve this with a final time of t. That means that my integrand should not, where's my partial? What am I integrating? It should not also be a t. You could do that, but it's kind of poor practice. So if that's my final limit, then what I really need to do is have something that distinguishes the other t's as being different. And that's kind of important. Okay, so I've changed my symbology a little bit. T0 is fine. Now again, so I'm just integrating this expression. Again, I just want to point out that if my upper limit is t, and I'm using that just because that's a nice and clean result, then I need to not have a t in the rest of it, because that's just plain confusing, although maybe engineering it like I just described is also confusing. It's the best I can do. Okay, and what is this? Well, sorry, let's bring to the other side. Wait, did I forget to multiply? No, there's still, what did I do? There's, this times this is this, but this isn't by itself, is it? Of course it's not. Sorry, it's easy to fix. It's still just here. Right, so it's a differential equation. The derivative is equal to itself. Sorry. All right, so, and then, what the hell did I do with the dt? Oh, no, I did get rid of the dt. Now I did that right. Sorry, right. Differential equation, the derivative is equal to itself, which implies that the answer is e to the something, right? Derivative of d is e. Okay, all right, now where am I at? And again, this is actually going to get kind of hideous for a second, but hopefully it's not terrible right now, I hope. Let's see, let me remind myself what's on the other side. Minus I over h bar. The limits on both sides need to make sense. So they're both going to be integrated with respect to t. So that means the limits need to be exactly the same, t and t naught and t. And then I've just got the Hamiltonian. And again, let's say the Hamiltonian is time dependent, because that's why I'm doing this, because you don't want to assume that it's not. That's why we have all this extra complication. If I have an upper limit of t, we want to make sure that I'm changing all the t's to t naughts inside the integral, because you really shouldn't have an upper limit also be in the equation. That's absolute nonsense. Okay, so there you go. Now, where we go from here is actually kind of easy. And then we're going to bifurcate in terms of the solution. A solution where the Hamiltonian is not time dependent, which I've already given to you, is relatively easy. And a lot of times the application of the time evolution operator is really easy. Most quantum problems, time evolving things, is actually really not too hard, surprisingly easy. And it's kind of cool that you can do that. And I'm going to show you how to do it on a computer. So like to do it for real, not just this ink on paper, which is not real, right? So programs that give you real results. All right, now what? How am I doing on time? Let's see here. I got to figure out where I'm at. Okay, that deal on top. The integral of the derivative of the function is the function. Maybe there's a constant, some constant that, remember when you integrate something, you're supposed to write the integral plus a constant because the derivative of the constant is 0. We're just going to drop that. You always just drop that in science whenever you have that problem. Okay, so what you end up with is the operator at t naught, minus the operator. Oh yeah, I forget how this works. Okay, that's on the left side. Right, so you see, again, you can see how I engineered the integral to work. So t naught is a constant, it's basically 0. And then I'm integrating the derivative, but there's a little t dash. T dash, the lower limit is t naught, and the upper limit is t, right? Right, it's actually just tremendously simple. Okay, but what's this? You actually should know what this is. It's a simple number. Remember, this is the time evolution. Oh, it needs a hat. That's why you don't recognize it. This is the time evolution operator, not evolving time. So therefore, it's what?
That is right.
It's 1.
Oh, it's 1.
No, it's 1.
Oh, because it's either 0 or whatever.
Yeah. Now, again, I'm going to do this at some point.
Yeah.
What you should recognize is that this is not evolving in time. This takes the state exactly onto itself. It doesn't evolve at even dt, which means it's the number 1. You cheated, but if I look in your head, but you get the same answer, right? So this ends up being 1. Now again, I warned you, when you look at this some other time in the future and you're just looking at your notes, it may be really confusing. And this is one of the reasons. Okay, now, and then I've got this jazz on the right, which I'm going to leave alone. I'm just going to write it again. I hate it when I get this position of having to write the same thing over and over again. Oh, I forgot my hat. So I'm going to do it quickly. Okay. All right, next thing. Okay, now this is where we come to a stopping point. I'm going to bring the 1 over there. And I'm going to then write this damn thing again, which I've already complained about, but I have to do it again. Okay, now I want to, okay, so now we're kind of stuck. We're not stuck, I mean, this is like kind of the answer. But now you got to learn how to go further with this, you have to learn how to interpret this. Because there's something really important about this. And as someone who knows how to do this practically, like when I take MBA classes, a lot of times our instructors have or still work in finance. And so they can tell us stuff like, you're learning some vocabulary and we're teaching you some principles, but we almost never actually use that stuff. It's just good that you know the vocabulary, you know the ideals, but when you get into the environment, you'll find that none of that's really going to matter. Okay, with that said, I can tell you that if I was given this and said, okay, MATLAB it, I am not going to go T0 is 0, or let's not be stupid, T0 is 0. I am not going to make that 1 second. Remember that long story I just said? I'm not going to make that 1 second under any circumstance. I'm going to make that 1 to the minus 17 seconds. That's the natural time scale for an electron. When I do quantum mechanical simulations of electrons, I make my time steps, not this time step, but this difference. I make that around 1 to the minus 17 seconds, 0.01 femtoseconds. Now here's why. A time-dependent Hamiltonian, remember, molecules move fast. The world to a molecule is going by on the order of femtoseconds. For us, 1 second to us is 1 second. To them, it's about 1 femtosecond. So that means that you are obliged to model things faster. If a molecule a second is a femtosecond, you actually need to be modeling faster than a second, right? You perceive things on the order of about 10 milliseconds. That's as fast as your brain can fire its connectors. From an input to a thought, it's about 10 milliseconds. So if I simulate you for a second, I need to be doing it in at least 10 millisecond time steps. So that's the idea. Okay, now with that said, what the hell does that mean? Okay, let's say that the Hamiltonian's a wave, a photon. Okay, that's a cosine. Let's make it a cosine. Okay, fantastic. Okay, let's say the H is like this. Let's make it a cosine. Okay, and of course, guess what? This is an electric field, and this is an electric field of a photon. All right, now, what's the integral of cosine? Is it minus sine or sine? I can't remember. Minus sine. Okay, sure, whatever. And let's say it's the same thing. Right, so this is the integral. Notice that if you get your time step, let's say you make t naught is 0. That's bringing it. So here's t naught. Let's say you make t right here. And of course, the effect of an integral is to take the upper minus the lower limit. What happened? From a mathematical standpoint, you took that number and subtracted that number, right? So what happened? It's like nothing happened. Does this ever report on any of this other stuff that happened? You see, if you are not careful with how you do these evaluations, if you go from here to here, the Hamiltonian isn't even dynamical. Nothing happened. You went from 1 to 1, or 1 to 1, whatever. It doesn't matter, right? That's my point. It doesn't matter. You need to have t naught to t done in small steps. Now, you would think that that's that job. No, it isn't. No, it's not. That's actually, dt is actually within, breaks up these brackets into small bits. But I'm just telling you the t naught to t has to be done in very, very small chunks. Because otherwise, if this is like wavy, you're just going to skip, it's like you're skipping over that. Okay, now with that said, what that means is that if I'm going to go from 0 to a femtosecond, I'm going to really go from 0 to 100th of a femtosecond. Then I need to put that back in here, and I need to do that about 100 times. Right, you follow me? Because if you want to do this accurately, you can't go from here to here. You have to take a small step. And that gives you here. That advances you a 100th of a femtosecond. Then you got to take that SOD and put that back in here, and then go another 100th of a femtosecond. And you got to do that 100 times. Now you've got a femtosecond. That's how you would have to do this. Right. And again, that's because the Hamiltonian is changing in time. Again, I know that because when I've simulated electrons quantum mechanically, and I'm telling you, you have to do it that way. All right, now, because at this part of the course, this is a pen and paper. You're going to be doing that, by the way. You're going to be using your computer, and you're going to evolve an electron's wave function in time. And you can visualize it, and trust me, if that sounds awesome, it is. But this part of the class is pen and paper. Okay, now get this. This is what you do. You're going to take this thing and put it in there. Right? And as I told you, this can be really confusing. And by the way, I can't really say that I think I can construct the integral correctly, but I'm getting to the point where I'm kind of confused. Okay, so now to do that, in other words, you have to break up time for all the reasons I just said. Okay, so what I'm going to do, this will be kind of normal initially. Okay. Now this is where we're going to go off the rails. What I'm going to do is I'm going to put this expression back in. This is now going to appear here, right? Okay, so now it's right, hopefully it's not too bad. 1 minus I over h bar. Now there's only one part that I got to get right. Notice that, again, in our integral engineering, I have to take t dash from t naught to t to get to that. I now have to integrate this thing to get to t dash. That means that my upper limit, my lower limit is still t naught, but my upper limit is t dash.
the t to t0 is like femtosecond, then the t dash is like again a division of that femtosecond type, right?
Yes. So what you're seeing me do is what I did when I took that graph and I cut it up into pieces. I've now cut it up into 2 pieces. And I have to do it 100 times. So, and you'll see what I mean in 1 second. Okay, now real quick. Now if I'm integrating, I can't have t dash. I have to have t double dash. Again, you got to be careful about the upper limit. Really should not. I mean, if you are really careful, you could do this expression and have t dash in here, but it could really get confusing. And then let's see here. This again, if we're integrating t dash there and t dash there, then if I have a t double dash there, then I have a t double dash there. Again, I'm just trying to be very practical and making certain that you basically write this out correctly. And now dt. Oh God, I made a mistake there. Sorry. Okay. And it should. Yeah, that's the reason I included it, because I had to have it in a bracket. Okay, so now I got integrals and inside integrals. Okay, now again, I hope it was logical. I hope you could follow along with my engineering the integrals to be, the representation to be correct. Now the thing is, you're going to do it over and over and over and over. Well, here, let me simplify this, and then you can imagine the answer is because, for all the reasons I just said, I have to do this over and over and over again. This is important. What I'm doing now is important because there's going to be a limiting form. It's like I'm going to be able to figure out a series for this. That's what I'm going to do next. So anyway, this is after you have done a bunch of manipulation and simplification. T double dash. Okay. All right, so that's after one substitution. Now you do it again. And again. And again. And now you're doing it to the nth, where n goes to infinity. So remember how we took the translation operator, just raised it to the nth power and let n go to the infinity. And then there is just a identity that you can Google that says, 1 plus ix is e to the ix, something like that. Sorry, 1 plus ix to the n is e to the ix. Something like that. I don't know if that's exactly right. But anyway, so when we did translation, it wasn't too hard. Okay, this is the equivalent. It's just that because the Hamiltonian can be time dependent, we're running into a certainly way more complicated expression, to say the least. Okay, now do it over and over and over again. Now you get this thing. This is called, I'll give you the name in a second. Okay, so here is truly the thing done an infinitely large number of times. So there's our infinity. So again, the reason I simplified it that way, so I didn't really need to do that. I just wanted this looks a little bit more digestible when I do that. This is from your book, by the way. Hold on. The double dash. Yeah, of course. Okay, T. I feel like something is, I think my notes have a slight problem. It's in your book. I think I've made a slight error in my notation here. Maybe I'll fix it with Photoshop or Illustrator. And -1. Huh? What's that?
The dashes, like, shouldn't it be T naught, or, T naught to T dash, or DT dash?
That's what I.
Yeah.
There we go, okay.
It's matched with, but.
Yeah, that's right. Okay. Right. And remember, these are just, this isn't to the nth power, right? It's just, it's a bookkeeping mark. And then that's belongs to this, dot, 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 and then you've got. And I think the idea is that if you do it enough, you can just forget this, like, you just don't write it down or something. I'm afraid that's what's happening. So you don't see u equal to u anymore, because again, remember, this is kind of unsolvable. When I have it equal to itself, it's unsolvable. So the idea is to break it up to a zillion points. And I don't know if t double, if you do it enough, that maybe it's equal to 1 because you're not advancing time anymore. But anyway, okay, so this is the expression. All right, this is a Dyson series. Okay. Now, a couple things about this. One, I've never seen anyone use this before. Cool, it's a formal solution. I've never seen anyone use it. I've seen, of all the professional talks, I've seen it mentioned once. In 20 years, I've seen it mentioned once. Yes, I remember what it was. And I don't even think the person who mentioned it even used it. Heads up on that. I feel I have a professional obligation to tell you about that, but regardless. Okay, now, if the Hamiltonian is not a function of time, which is fairly frequent, right? So a molecule, if we're going to do time dependence on a molecule, let's not shine light on it. Let's not put it in some kind of contraption, a flux capacitor that's whizzing some magnetic field on it, right? If we choose not to do that, which all around us, that's what's happening, there's lots of practical questions that can be answered without time-dependent Hamiltonians. Then what you end up with is this. And I almost forgot the head. Okay, and again, I think this, I'm just like stealing this from the book at this point, like writing down stuff from the book without, I've never used this before. I've never used these expressions, and again, I'll show you the practical expressions that I use when I do this for real at the end of the class, and I think you will find that a lot of fun, by the way. So I can't say that I don't really feel like I totally get this, to be blunt. Again, because I've never actually used it. Okay, so this ends up all being, by itself, this is t minus t naught to the n, where of course it goes to infinity, over n factorial. Okay. In which case, it ends up being 0 to infinity. And now we are at an expression that you just look up on a Google search of like series, functions and their series approximations. And guess what? All right, h bar t minus t naught. And to make the units work, you better divide by h bar. And here's our guy. What did I do? There we go. And real quick. I know you guys know. Let me show you how easy this is. You know that since this is a function of an operator, so let's say that you have the operator operating on its ket. If the operator, so this A dash is a eigenket of the Hamiltonian, check this out. To evolve A into time, just to use the language I used before, it's this. Where E dash is like, like an electron volt. T naught is 0, so that doesn't matter. So you take your state, and now, again, let's even be more practical. That's the ground state of the particle in the box. This is basically, I have to act on it with the bra. That's sine pi x over L. That's sine pi x over L. To evolve that in time, I take e to the energy, it's like an electron volt. E to the minus electron volt over h1. And I multiply that. And that's how I evolve it in time. Ta-da! You don't like the I? Make that cosine plus I sine. Times the wave function, e to the minus x squared, sine pi x over L. Whatever, right? We have some simple wave functions to work with. And as long as it's an eigenstate, this is nothing. It's a joke. And most of our questions are this easy. And occasionally they're not, which is what we'll get into later. Anyway. So there you go. That's a handful. Oh God, look at all that. Oh, it's impressive, isn't it?
Don't erase it.
Dyson series. The most important thing about a Dyson series is that it sounds really cool. There you come on, Dyson. I love Dyson series today. Awesome.
Quick question though. If you take like the Hamiltonian, like, and it's not a function of time, and what you wrote under that, does that reduce a Dyson series? Because it looks like a geometric series, like after you do that. Right?
No. Dyson series, if time is not, if the Hamiltonian is actually in fact not time dependent,
Yeah.
is here.
It's basically like a geometric series.
It's
right?
here. It's here. Yeah. No, it all follows. It's just that if it is time dependent, you're stuck.
Right.
You're stuck here. You deal with this in the form that it's in. But if it's not time dependent, I'm just showing it reduces
Right.
to this form.
If you're programming, just write one program and put in a loop for the time interval.
When I show you how to do this for real, it's even easier than that.
Yeah, it's because
That would like make the computer
just
slow.
changing the time intervals, right? So you just put one integration and put a loop.
Sure, but again, I can't emphasize enough. There is a way to do time evolution, which I'm going to show you, that is even simpler than what you just said. I can evolve a three-dimensional object in time with 4 lines of code, 4 lines of MATLAB, and each individual line is only like 10 letters.
Well, because to run the loop, wouldn't you be like murdering your processor essentially?
So I have a paper coming out where I use this stuff. A paper's coming out where I use this stuff, and it took a couple of weeks on a really fast desktop.
But we are using femtosecond here,
Right.
They're not trying to do it 1 minute or something. That is fine.
Again, I'll show you, I'm not trying to be difficult, it's just that it's hard to do. I'm going to show you how to do this for real, and I'm going to give you real problems, and you're going to see how easy this is, but I don't quite have the ability to tell you that yet. We have to live it. It's like looking at the Grand Canyon picture. I remember looking at that thinking, okay, that's cool. And then I saw it. I was like, that has nothing to do with looking at a picture. It's the same place, but the experience that you got